So fuel systems on transport aircraft, these are one that overall have similar elements to smaller aircraft that you've learned about in basic systems, but they are significantly more complex just because of the amount of fuel these planes have to carry and use. So they're covered in ATA Chapter 28. So when you're looking for manual references and that kind of thing, that's where you'll go. And there it is. So broadly speaking, just like any other system, fuel systems are made up of a collection of subsystems. And they're typically broken up into about 5 different ones. So the first one is storage. We have to put the fuel somewhere, tanks and that kind of thing. Refuel and defuel, how we get it in. This is one of those areas that's significantly more complex than small airplanes. Small airplanes, they just have a hole in the top of the wing and you dump fuel in, right? They do have that, but it's not the most efficient way to fill them. They have to have more complex vent systems because we are moving so much fuel around. We don't want to pressurize the wings and pop them when we're filling. We don't want to pull a vacuum in the wings or the fuel tanks while we're using the fuel and crumple things like a tin can. That wouldn't go over well. So they have to be vented properly. We also want to make sure we don't spill fuel in the process of venting them. And then we have to provide indication in the flight deck. And again, we're dealing with multiple engines over longer distances that are using much larger volumes of fuel. So just kind of monitoring, fuel flow and that kind of thing. We gotta look at level. The fact that fuel sloshes around and moves means we have to have fairly complex systems to have a very accurate level reading, much more so than a small airplane. Has anyone seen the fuel gauges in like the Cessnas when you've taxied them or moved them around? You ever watched the gauge? What do the gauges do? They just bounce all over the place. We don't want that on a big airplane. Yep. Yeah, it's like, it's got hydraulics and stuff. And then finally, distribution. We got to get that fuel to our engine somehow. We got to make sure there's enough of it. These things burn a lot of fuel, and so they got to move that high volume of fuel quickly, and they have to ensure that that distribution doesn't get disrupted. So each manufacturer, however, may break these down slightly differently. They may combine some. In some cases, venting is kind of tied into other systems, like possibly refuel, defuel, in different ways. So some have more or less kind of subsystems. Some they call them slightly different names. But we're going to start with fuel storage. So fuel storage, transport aircraft, almost exclusively across the board, utilize integral, what are called wet wing tanks for the main tank. And that is, the primary places fuel is stored is in the wings. The wings themselves, the structure is sealed. There are no bladders. There are typically no bladders or metal tanks inside or any kind of liner. It's the inner surface of the metal that makes up the skin. The inner surface of it is the fuel tank. And so all the rivets, everywhere they're riveted or composite structures that are bonded, those all have to be sealed. There are access panels typically on the bottom of the wing. Those have special seals that not only seal the fuel in, but they provide electrical bonding so you don't get static buildup and that kind of thing. And so it's the fuel primarily is stored in the wings. It does often go into a center belly tank, but depending on the aircraft, there may be 2 or 3 primary tanks. So in a 3 primary tank configuration, you're going to have a left wing, a center tank, and a right wing. This airplane here, we'll look at it. This is a 2-tank airplane. In a 2-tank airplane, you have a left-hand wing and a right-hand wing, but those they extend into the center fuselage area, as you can see here. There's still a fuel tank in the center, but they're mainly divided left and right in this 2-tank version. But we'll look at 2 and 3-tank. And then some planes, especially if they're larger, may add auxiliary tanks, and those can be in quite a few different locations. So in some cases, auxiliary tanks may actually be in front of or behind the center tank, kind of where the cargo area is on the 727, the lower cargo deck. If that has its auxiliary tanks, they're just in front, and behind they take up room in those lower cargo decks. Other planes will actually can sometimes have auxiliary tanks in the horizontal stabilizer. So the stabilizer itself kind of does a similar thing. They can also have what are called saddle tanks, and that is a tank that kind of follows the contour of the fuselage, often back in the tail area. Can either be above or sometimes below in the bottom half, or both. And they may have multiple. So depending on the aircraft allows, but for the most part, you're going to see these main tanks in the wings. Anyone know why, if I were to ask, why do we carry the fuel in the wings? There's a couple reasons. What are the reasons we carry fuel in the wings? Yeah. Well, that's where the engines are in most airplanes. Now, even in airplanes that have tail-mounted engines, we still carry it in the wings. But for those where it's in the wings, it's close. It's free space, right? We got that space we can use. Yeah. It distributes weight within the lifting body. So fuel that is in the wing is right inside that thing that's lifting the plane up. Fuel that's in the fuselage, that weight has to be transferred through the connection from the fuselage to the wings. And so a big part of it is we can carry a lot of weight inside the wings to minimize stress on that wing joint. And in most of these, we'll talk about if in a 3-tank or a plane with fuselage auxiliary tanks, those are going to be burned away first to minimize the amount of weight in the fuselage before the wing tanks start to kind of burn down. Other things inside of these, kind of some parts we'll see, is there's always going to be collector tanks that are near the wing root or center line of the aircraft. And these are shown, these 2 red ones right here. And we'll talk about the purpose of those. And then surge tanks are going to be near the wing tip area. And you can see these don't extend all the way out to the very tip, right? The wings get pretty thin at the tip, fairly small. There's minimal space out there. So we don't need, they won't go all the way to the very tip of the wing because this area is just too small. But the surge tank is going to be connected at the near the ends. And so here's a bigger version of that. You can see again, this is a 2-tank aircraft. If you had a 3-tank aircraft, this area in kind of purple pink would be the center tank. The collector tanks would often still be on the inside, but they would be plumbed to the wings, not necessarily to the center tanks. They'd be like an extension of the main tanks inside the center wing box. Okay. And the purpose of these is the main tanks, the main wing tanks, feed into the collector tanks. These are dihedral wings. They're up at an angle, right? So fuel is going to flow downhill. And fuel is going to flow downhill. We use gravity and sometimes some what are called scavenge pumps or certain types of boost pumps to move fuel from these wing tanks into the center tanks. Okay? And as the reason for that is fuel can flow from the main tanks into the collector tanks, but it cannot go the other direction. And the pumps and the boost pumps and the fuel pickups for the engines are going to be located in those collector tanks. And so what that allows is when the plane banks, especially if it's an uncoordinated turn, or if it goes into a sustained bank or into an uncoordinated turn, that wing that's down, the fuel's going to want to slosh away from the center of the airplane. It's going to want to slosh away from. So that collector tank is designed to maintain enough fuel to feed the engines for the duration of a bank or uncoordinated turn until the plane levels back out and fuel can slosh back to the center again. So it keeps the fuel pumps in liquid fuel the entire time. If we have a 3-tank aircraft, what ends up happening is the center tank tends to feed into the wing tanks. And so fuel is moved from the center tank to the wing tanks first. The engines still are going to draw from the wing tanks via the collector tank. But we're going to keep the wing tanks full as we move fuel from the center tank out to the wings. And again, that's to reduce that stress on the wing fuselage connection point. Okay? In a 2-tank aircraft like this one, these center tank areas are just an extension of the wing, so fuel just drains downhill and then into the collector tank. Okay? But if you have a 3-tank or more with auxiliary tanks, you want to burn that down first. But it doesn't go, oftentimes it doesn't go directly to the engines. Some cases it can. A lot of cases it gets pumped into those wing tanks and then fuel is pulled off the wing tanks through the collector tank. The last part, out at each tip there, I talked about the surge tanks that are here. And the surge tanks are essentially a dry bay. They are not meant to be filled with fuel most of the time. They are there they are the connection point typically for the majority of the venting system. So they act as a break between the liquid fuel and the venting system to help prevent fuel from getting into the vents and ultimately leaking out of the airplane. The other thing they'll do is, for the most part, fuel can't get in them unless it kind of goes over the very top of that divider. And so they will catch some of that surge that may occur in a roll. And then the fuel drains back into the main wing tank. So they've got check valves in them that allow fuel to move inboard. And if you get a big surge, if you get a big slosh of fuel, like a wave, think about how much power there is in a wave if you've been to the beach, right? That can actually, waves in a fuel tank, sloshing like that, can cause damage to the structure. If any of you are familiar with the Concorde, everyone know what happened to the Concordes? The Air France Concorde that crashed, kind of ended the flights of the Concorde. That was doomed. What actually broke that, it hit a chunk of metal on the runway and it burst a tire. The tire flew up and hit the wing, the bottom of the wing. That was not actually what damaged the wing. Well, it damaged the wing, but it was not what caused a breach of the wing. When that tire hit the wing, it sent a shock wave through the fuel. It sent a pressure wave through the fuel. And that pressure wave actually burst the wing outward. So it wasn't the chunk of tire going up and in. It was the shock wave in the fuel that came back down, and it basically popped the bottom of the wing right behind the engine, and then the fuel caught fire from the engine, the exhaust of the engine. And so surge tanks kind of prevent that from happening when fuel sloshes. Normally it's a spot where that energy, the fuel can dump over into it, dissipate that energy, and then that fuel is able to run back into the main part of the tank. But it also serves as that dry bay to separate the venting system from the fuel, so we don't get a bunch of liquid fuel going out the vent system. Another way to look at it is like this, and even the tanks themselves, the main portion of the tanks, are divided into bays. Okay, so this is that 2-tank aircraft, divided into left and right. These are the surge tanks right here, or sorry, excuse me. These are the collector tanks right here in the middle. And then the surge tanks in green out here, and then you can see the vents outboard of it. Okay. And so fuel, these are all these little red things, are check valves that allow fuel to flow in towards the center. So fuel in this case comes from out here. If fuel gets out here into the surge tank, it can drain back into the wing. For the most part, fuel that's been filled in the wing is going to work its way inboard. It's going to work its way inboard. It can go into the collector tank. This is still part of the main tank up here in the front, in the center. But you can see then fuel goes into the collector tank, and there's no way then, these are check valves. They don't allow fuel to go back out. They go the direction they're kind of pointing. And so fuel can't leave. It can't go from the collector tank back out towards the wing. From there, the fuel pickups are in that area, the boost pumps and motive flow pumps and that kind of thing we'll talk about later that feed the engines. Okay. Other things you'll see in here, so flat valves and check valves kind of do the same thing. They've got these little oval check valves, flat valves, pretty much do the same thing. There are a couple drain valves here too. You can see in the wings, there's one here and here. And then the collector tanks are here and here. Those are basically the low point of the wing and the low point of the collector tanks. And they allow us to remove water and other settled contaminants from the bottom of the wing. It's a little valve on the bottom of the wing. Just you've used the sumps on the smaller airplanes, works exactly the same way. You push a pin or a screwdriver type item up into it. It opens, fuel starts running out. If there's water in there, that should come out first. And so those are in the low points. So there's not much, everything here is, there's no power really. There's nothing in the tanks that kind of moves the fuel around besides primarily gravity. We primarily, feed fuel from tank to tank in most cases using gravity. Now with all these tanks and with this fairly complex setup, there's a lot more than a small aircraft. We have to have a way to fill this all, and we have to be able to fill these quickly and efficiently. Most airliners, small regional airliners, they try to do a turn. Flight lands, people get off, new people get on and go. They in some cases are doing turns of 25 to 30 minutes. So that means plane land when it pulls into the gate. So 25 to 30 minutes at the gate. People have to get off. Bags have to be unloaded. New bags have to be loaded. New people get on, and the plane has to be fueled and ready to go. And so imagine if you were doing overwing fueling, this would take a long time to go around to each one of these tanks in different areas and fill it up. So what most of these large aircraft have are what are called all of them, I shouldn't say most, all large aircraft have pressure single point refuel defuel, and it's almost always located in the right wing. Why in the right wing? Or the right side of some have it in the right side of the wing root area. Because people get on and off on the left. You'll notice most airliners, most transport aircraft, they're set up for service on the right, passengers on the left. Right? You got a jet bridge or loading on the left, the right side. That's where the baggage that's where the baggage doors are. That's where the fueling receptacle is. That's where the galley, where they bring the galley carts up to service the galley. And so they put these on the right, and they may have planes, some of your bigger planes, some of the largest planes out there, A380s, 747s, they may have some in the left wing as well. But for the most part, if they're going to be fueled anywhere, it's going to be the right wing. Small planes will have single point refuel, defuel. Larger planes, the 727 we saw, actually had places where you could hook up 2 hoses simultaneously. Very large airplanes, sometimes you can hook up 4, and that would be 2 in the right and 2 in the left. Okay. And what they've got here, instead of a fuel cart, large airports, they've got an underground fuel system. This is just like a little pumping cart. They hook it up to a port in the pavement, and it pumps fuel up and into the wing, rather than bringing a fuel truck up every time. So while we're doing it, we have to be able to control where the fuel goes. So at that area, right in this same spot, there's going to be a fueling panel. We saw the one on the 727. Okay. And how many switches are there on the 727 for tanks? 5, right? It's got its 3 main tanks plus the 2 auxiliary that are removed, right? So that had 5. When you have a 3-tank or 2-tank aircraft, they're typically going to have 3 or 2. So here's a 3-tank aircraft on the left. It has, it's hard to get a good picture of this, but you basically have a power switch to be able to turn the panel on until you're going to operate. You want to be able to make sure everything works on it, that all your lights work, all your displays. These are numerical displays. They're kind of hard to see. So you can press that to make sure everything lights up properly. Often they'll have newer ones where there's computer control. They'll have a byte test button, built-in test equipment. And then a few other controls. So 727, that was all auto. You saw the valves, you had to open the valves, watch the gauges, close them. Newer planes now, it's automatic. So on something like this or this, and this one here is a 2-tank. You can see there's a left tank and a right tank. And it can be run in auto or manual. It's got the refueling on and off. This one also has a defueling option, which this does too. There's a defuel option here for the 3-tank. And then a test switch and a quantity selector. So what you have here is typically if you're going to refuel, you would put it in auto and you would set the total quantity here. And the airplane, what it'll do is it will automatically fill the wings first until they reach their max level. And then if you've selected a volume, or a weight, because we do fuel and weight, pounds. If you've selected a weight that's more than what the wings hold together, then it will start to fill the center tank on this one. So if you look at it right now, it reads, and this one's in pounds, reads I think about 410, 340, it's really low, and then 0 in the center tank. So if you were to auto fuel this, it wouldn't put any fuel in the center tank until the wings reach their max. On this one, this 2-tank aircraft, it doesn't even show normally all the tanks. It just has a total fuel quantity. So you can set how much fuel you want, and you turn the fueling valve on, and then these lights will come on to tell you what fuel is going where, and then it'll tell you what the total is. But that's a 2-tank. The assumption is it's going to load the left and the right tank equally. They can both also be run in manual. If you put this in manual, here now you have 3 shut-off valves to be able to route fuel to one tank or another. And you can see right now it's set in manual, and the shut-off valve for the left and the right, which these are reversed just because the way this panel is. If you're looking at the airplane, if you're looking at it, it's on the front of the wing, so you're facing the front of the airplane, so left is on the right and right's on the left. That's why they look backwards here. You can see this right wing tank, it's open right now. Left wing tank's open, center is closed. So there's fuel being put into the left and right tank right now. And then, like I said, this also has the option to be able to defuel to suction fuel. And same thing happens here. This can be put into a manual mode. And then it also has a defuel option here. Okay. The actual point where the fuel comes in, the receptacle, we've got 3 basic parts to it. So here's what the end of a fuel hose looks like. And that will mate with this receptacle. So we saw this 727, you could see from this part to the left, right? You can see this flange left. There's a check valve inside of there that ties into the fuel manifold. This fuel hose end slides up. You can see there's 3 kind of tines here. 1, 2, 3 that'll go into these 3 slots on the fuel hose end. Turns about 45 degrees, locks in place. That opens this valve and the valve in here. There's a check valve on the end of that too. And then fuel's able to go in. To cover this when we're not using it, you have a fuel cap that looks like this. And which group, who was in the group where I got fueled? Yeah, so when you press this trigger right here, there is a vent on this cap. And if there's fuel caught between in this area right here, or if that check valve's leaking, when you press that button, you'll get fuel dumping down on you. So my pants still smell like fuel. I wore them yesterday and I smelled fuel all day. So there's what the cap looks like. Where that's going is into a fueling manifold. And this is probably the simplest manifold I've ever seen. And right here you can see, so the right side of the plane, again, it shows the right. It's on the right. There's a refuel. And this one is right at the wing root. It's right on this plane. It's right where the wing ties into the fuselage rather than further out on the wing. But you've got your single point adapter. Fuel can come in. And then you've got 3 valves, a valve for the left, a valve for the right, and a valve for the center tank. And this is the one that's controlled by this panel right here. So those 3 valves can be controlled automatically, which is typically how fueling is done, or they can be controlled manually if need be. And then they can also be opened and defuel. Do you see a problem with defueling with this? What's lacking on here to allow it to defuel? No, the vents aren't shown. Okay, yeah, so it's got this, it's kind of a 2-way check valve. It will open in reverse if a certain thing happens. How would the fuel get from this tank up out here? Do you see a pump anywhere? Suction. So the fuel trucks have the ability to suction fuel. Okay. Some planes do also have pumps, or the pumps can be tied in where you can assist defueling using the fuel pumps. Some aircraft, it's purely done through the suction that the fuel truck can generate. So this one, the fuel goes in there. You can see there's what they call a high level sensor in each one of these tanks. It's a little deceiving. These high level sensors are going to be out near the wingtip, just inside of the collector tank. And essentially what those do is they're typically hooked directly up to these valves, where if fuel contacts that high level sensor, no matter what the computer is telling it to do, no matter what the switch position is, they will trip these valves to the closed position so that you can't hopefully overfill the tank and have fuel come pouring out of the different vents. Here's a 3-tank aircraft, a little bit more complex setup. This has a pressure fueling station. There's two ports in this case that go into a manifold. Okay. This tank has a dump system. You may recognize this. This tank has a dump system, or fuel system is a dump system for overboard dump. Okay, tied into that. But you can see there is fuel enters this manifold, and you've got fuel shutoff valve. So here's the shutoff valve for tank 3, the right wing, shutoff valve for tank 2 in the center, shutoff valve for tank 1. This has another thing on it. As the fuel comes in, some of it goes through this thing called a compensator wash line. And we'll look at compensators later. That's a part of the fuel level indicating system. And by directing fuel across the different sensors while fueling's taking place, it essentially cleans any crud off of them that's building up and helps to keep your fuel sensing system from having issues from stuff building up on the sensors. So that's what those wash lines are doing, is directing a jet of fuel against the fuel sensors, the fuel level sensors, to keep them working properly. It's just something kind of unique on here. Okay. The other thing you've got here is a fuel manifold drain valve. You can see comes into the left wing. What actually happens is this is designed where when you're done fueling, any fuel left in the manifold is supposed to be able to drain down into that left wing, just so you don't have a bunch of extra pressure. You don't want to leave this pressurized all the time. There's the compensator wash lines I was talking about. And then the fuel dump system, there's ports that go to that as well in this case. 2-tank aircraft, here's that same 2-tank aircraft. Our fueling port in green here, and there's a shutoff valve for the right and for the left, but you can see there's nothing in the center here because, again, these center tanks are part of the left and right. There is no separate center tank in this aircraft. You do have, though, in this one, a defueling shutoff valve. Okay, so there is a way to remove fuel from the tanks that are at the lower point of the wing using that shutoff valve right there. Some of the other things now, we're starting to see some venting on here. The blue is venting, and the ability to do that. So while these are operating, here's that panel. We saw that panel. You can see this panel is able to control our fueling valves, the crossfeed valve and fueling valve. Okay, so pressure refueling. So right now it's set up for defuel. And so there are auxiliary pumps that can feed into this in order to pump fuel off, as well as that kind of center pump is able to as well, the DC motor pump there, to be able to assist in it. But this system will work, will allow defueling using just a suction truck as well. If all this is not working correctly, if we have to defer it, we still do have the ability to fuel the airplane using what are called overwing or gravity. And this is exactly the same as how we fuel the Cirrus, the Cessnas. These are much smaller ports that they can get up on a ladder. The fuelers get up on a ladder and put fuel in. It is very slow to do this. It can take hours on a large airplane. So they really aren't used too often, but they are there. So if we're performing gravity fueling, most of the time it's only it's not for normal operations. Occasionally we would have a plane out flying that was needing to be gravity fueled. The fuelers hated it because it is a pain and it does take a long time. You'd get a lot of delays because of it, but it is there. And these caps work just like the other ones. You lift the tab, quarter turn, that unlocks it from these tabs. It opens to close it, fuel cap in place, turn this little lever about a quarter turn, and then lay it flat, and it locks it in the flush position. One thing we did have to do is always make sure that these were flush, and though they can often be put in any orientation, they can kind of go three different ways because you've got three locking levers. We always tried to have them installed so that the tab was laid down facing aft. And that way you didn't have the slipstream trying to pop it up. Okay, if it did start to pop up, it would get pushed back down by the slipstream. So the venting system is there to prevent, we need to let air out of the tanks when we fill them. You know, we put a bunch of fuel in there. There's air that the space has to be taken up by. It's also there as we use the fuel. We don't want a vacuum to develop. Vacuum developing in the wings, one, it could impede the ability for fuel to flow to the engines. Right? It's gonna make it harder for that fuel to flow to the engines. The other part of it is it could put structural stress. You know, it's gonna try to collapse the wing and try to collapse the structure. So both things we don't want to happen. So you're going to have vent systems in various areas. So in some cases, on this aircraft, for instance, the vent system is not actually connected to the surge tanks. There's a separate vent for the surge tanks. These have tank vents, and you can see there's vents. These are near the top of the tank. And there's one in the wing, left wing, and one in the right wing. They're a little bit further out in an area where it's most likely to have air in the tank. It's at the highest point of the tank. But you can see that these lines, these aren't mistakes that they drew where they kind of go up, these vent line tubing. They do make a pass. They actually went up into the side of the fuselage and then back down. And that way, if fuel does get in them, it prevents, they're tall enough that fuel shouldn't be able to make it up over the loop before it gets into this half that eventually goes out to, out to the vent right here. Here's the air scoop, the vent. Okay. If fuel does get into it though, this is a low point in it where there's a little purge line. This is a little scavenge ejector. It's an ejector pump or a Venturi pump that creates a suction on here to any liquid fuel that gets down in here will get sucked and get shot back into the tank. Okay, so these vents here do not connect to the surge tank. Then there would be a second vent that basically just connected to the surge tank, straight to it. There wouldn't be any additional, it would be an opening from the surge tank out to the atmosphere, connecting to the very top of the surge tank. A couple other things we'll look at. You can see that there's some relief valves here. Those are kind of a backup system, and we'll look at what those look like. Those can open if this whole venting, the main venting system here gets plugged. Those relief valves can pop open. In this case, they're positive or negative pressure, where they can open and allow air in or out of the tank, but they don't have a way to capture fuel, so they will leak fuel in the process. They're located high in the tank, so hopefully the fuel is down below them, but they don't have, you may get some fuel liquid, some vapor, or other stuff that can escape through them, but they shouldn't open over the course of the life of the aircraft. If everything works right, they should never actually have to open. We would test them, we'd go up and physically make sure that they'd open every time. Because again, they are designed where they're connected, where fuel should never be up to the level where it's actually in those. With all of these, you can see at the end here, there's a vent flapper, there's a check valve. Some of them have these ones in the center tank where they have to be below the fuel level at times. There's a flapper check valve. The ones out here are never below fuel level in theory in the wing tank. So a flapper check valve is just a float that looks like this. When the fuel level's low, the float drops down, is able to opens the little vent. When the fuel level comes up, it just pushes it closed. So very simple, mechanical, doesn't require any monitoring, doesn't require any, every once in a while we would make sure that they weren't stuck. But other than that, there wasn't much you did with them. Looking at a little bit more complex venting system. In the main tanks, You've got vents that connect the various bays. Now remember, these are all connected. These kind of manila areas and then the light blues. These are all connected together. Fuel can flow from one to the other. But at the top of them, we have them connected together with tubes that provide venting. And so air can vent from these center areas to the wings, and then from the wings out to, in this case, the collector tanks. You can see collector tank on the other side. Sorry, the surge tanks, not just surge tanks. Collector tanks are in the middle. You can see they're not really vented. There isn't really a need to. They're considered full all the time. And then the surge tanks out here where air goes to it. So if we look at one side a little bit closer, the air that can go in and out can travel through these tubes. It comes from a big NACA scoop out on the wing, and the surge tank has a NACA scoop coming off of it. And a NACA scoop are these things that look like this. So these are on the underside of the wing, but they've got this standpipe that goes to the top of the tank. And these allow air in and out for the most part. But in flight, they actually provide a certain amount of pressure. So our 727 has them as well. You can see these big scoops on the bottom. So hopefully, have you all seen NACA scoops before? What's the point? What's the purpose of them? Why are they special? They provide ram air. Okay, but I could just put a scoop on the bottom of the plane and get ram air. But they minimize the amount of extra drag. So they're flush and then set in rather than a scoop that sticks out. Okay, so they minimize the amount of drag that they produce. So in flight, these are going to actually have air being rammed in, and it's going to provide a small amount of pressure, small amount of head pressure in the tanks. Why do we want head pressure in the tanks? What's that going to do? It could help prevent fuel vaporization, although that's probably fairly minimal because up at altitude that's cold, you're not getting a lot. Well, it's actually created, well, that's why they're venting. So they're vented so that the pressure stay equal as fuel's used, as the airplane changes altitude, all that. Why would we want a little bit of positive pressure in the wings while we're flying? What's that going to do? It's going to aid in something. It's going to help aid in the fuel flow. It's going to push fuel into the feed system to help move fuel towards the engines. Okay. So it's going to assist the pumps by having a small amount of pressure there. Okay. So the venting system isn't just a passive system. It's going to actively help in feeding fuel to the various parts of the engine. A few of the other valves that you'll see over and under pressure relief valves, I know they're not the greatest, but you've got negative pressure relief valves. You can see these are on the bottom of the wing. These are the fuel access panels. So when I say access panel, it's these oval panels kind of on the bottom of the wing, right here. Here are your fuel bay access panel. So those allow air to come in if all of a sudden the wing's getting a negative pressure, primarily during defueling would be about the only time they should open. If the vent system can't provide enough airflow in, these can. Even still, these NACA vents pull quite a bit of air fairly quickly. You have positive pressure relief, works kind of the same way, but these are on a standpipe, so they're near the top of the tank. So there's no, if fuel is up there and this opens, it is going to have fuel come out of it, right? It doesn't have that isolation going through like the surge tank or some kind of a gravity loop that goes up the side of the fuselage. But again, they should only open in extenuating circumstances, not under normal operation. And then a third one you can see here is an overpressure relief burst disc. That's not a valve. All that is, it's a metal disc. It's had score marks put in it. And if you get one of those shock waves traveling through the fuel, it will burst. The whole point is it will pop that disc and allow pressure out. Now, it'll probably dump fuel along with it. But if a plane's in flight, like I talked about with the Concorde, and a shock wave, something hits the wing and it causes a fuel shock wave, they are located where they're not going to cause a fire hazard. Just kind of like the dump system, that's out in the wings where it can dump fuel away from the engines and away from some kind of an ignition source. So this burst disc can pop, and it does have a standpipe. Hopefully, it's above the fuel if it does, but if it's not, there's nothing there that's going to prevent fuel from running out of it. But it's better than having the wing pop open, so to speak, at a spot where there's potentially an ignition source, say right behind the engine, which is what happened to the Concorde. Here's a normal access door they're showing. And these do bolt on. They've got captive nut plates that are sealed. So when the screws go in, they're sealed and riveted to the structure. And then on this edge, the edge where these interface, there's like a wire mesh with inside of a rubbery, it's almost a gel seal. And that wire mesh, when you clamp it down, that wire mesh contacts the metal of the wing skin and the metal of the panel so that they're electrically bonded. So you don't get a static buildup across the two that could cause an arc. You wouldn't want a static difference between your panel and your wing skin and have that arc across where the rubber seal is and create an ignition point. So the seals on these are all, it's this really weird, it's like a blue, purple gel kind of with screen. It almost looks like window screen embedded in it. And they're a one-time use thing. When you peel them off, they just get this, the gel just kind of breaks apart. So you put them on, and when you tighten them down, that metal mesh that's inside of there will contact the two metal surfaces and bond them together. So there's that overpressure relief disc I talked about, negative pressure, positive pressure. Here's another view of a pressure relief valve. You can see what it looks like on the outside of a panel. It's just kind of, it's flush, really doesn't, pretty unobtrusive, but they are designed where you can go up and kind of push on them to make sure that they'll open. It's essentially just a spring-loaded check valve inside of there, is all it is. Pretty simple. The spring holds it shut. If you get negative pressure or pressure, it can pop it open. And oftentimes they're built into our access panels like this so that they're easily replaceable. In fact, we would have access panels with these already attached. If we had one of these go bad, we would actually just typically swap the whole access panel because you had to open it anyways. Swap the access panel and then replace the pressure valves. Send them to a back shop to have the pressure valves changed out, because at that point you got to put a new seal on here and everything else. And when you're dealing in an airline environment where you got to get the plane turned, you often put stuff in the back shop that doesn't need to be done on the shop floor. And here I've got, it'll open if you have a three pressure, it's PSID, pounds square inch differential between the inside and the outside of the wing. And that's when these will pop open. So I'm going to stop and we'll take a break there.